Merci. Alors, ça marche. Ok.
Normalement, après c'est direct.
Oui.
Donc le temps que ça s'installe les drivers, c'est sous le nom.
Ok.
Maintenant, tu peux passer les slides avec.
Non, mais c'est bon. Ok. On commence? Ok. Hello everyone. Thank you for your presence. My name is Pedro, and today I'll be presenting my work at the PhD here at the LVA, entitled Coupling Sonic Black Holes to a Resonant Cavity, Numerical and Experimental Insights made in a quantitative agreement between the LVA and the Human Environments Research Group at the La Salle, Barcelona, and with the supervision of Professors Laurent Maxi and Noël Wasque from Barcelona. So to start with a brief contextualization of the SBH, from the original concept, SBHs are wave retarding duct terminations that obey a parallel profile and that present a varying admittance that slows down waves to a singularity point at its end, ideally. And as you can see here in the SBH governing equation, when x equals 0, thus at the origin, we have a singularity point, and then that prevents a reflection of the waves. So if the smoothness condition is observed, that means that over a certain cut-on frequency, the SBH is going to be operable. However, as you can see in the figure from the right, the most, let's say, famous practical SBH concept is that of waveguides with concentric rings with radius that obey the parallel profile. And there's a big difference between these concepts and these concepts, obviously. We have profile discontinuities, we have a finite amount of rings, the rings have thicknesses, and there are also a truncation at the end, and cavities are formed in between the rings. So the absorption mechanisms of a practical SBH are in the end very different than the absorption mechanism presented of the ideal concept. And for this reason, other than modeling, literature has been investigating damping mechanisms and ways to increase the absorption inside an SBH. But the thing that all papers have in common is that all of them consider SBH in ducts. So having this context at hand, our motivation here with this project is to explore SBHs for noise reductions, for noise reduction inside rooms and cavities. So if you take a general system of a homogeneous cavity with an inner source and attach it to a given number of SBHs, we know that this coupled system is gonna have a quite intricate dynamics, and this dynamics is gonna be tricky to numerically characterize. So thinking about that, our goals are to design a numerical tool based on the substructuring technique named patch transfer function, or PTF, to obtain the response of the closed cavity when coupled to a set of sonic black holes, and to evaluate if the sonic black hole is a viable solution to the sound problem in a cavity. These two first goals are related to the first paper produced in my PhD, which has already been published. And finally, we also have the goal of validating experimentally this PTF strategy for the cavity plus SBH problem, which is going to be related to the second paper, which is loading at the moment. So let's start a bit more in depth about the first paper, which is entitled Coupling Sonic Black Holes to a Resonant Cavity Using Patch Transfer Functions. So talking about a bit more about the PTF, this method consists of dividing a mechanical system into subsystems. And at the surface, in between the subsystem, we divide this surface into patches. And then transfer functions are obtained at those patches to characterize both subsystems individually. And then continuity conditions are applied at those patches to recouple the system and finally get the characterization of the coupled system. Obviously, a few hypotheses must be observed for this PTF method have physical meaning. So we have to suppose that the coupled system is linear, so superposition of effects applies. There's a limitation of size to the patches that's related to the minimum wavelength involved with within the range of frequencies that we are analyzing, and the shape of the patches can be different than the real coupling surface, but the area must be equal. And also the patches are considered rigid, so the velocity and pressure at all patches are always constant. So now for talking a bit more about the subsystem of the cavity. If, for example, we have here an example of dimensions that were investigated. We're gonna compute the transfer functions of impedance that are gonna characterize at the end this subsystem. So we're gonna have three main impedance forms that are gonna dictate how we're gonna find the dynamics of this subcavity. So it's gonna be the impedance between patches. So here we have only one, but we can have many patches, and it's gonna be the mean pressure at one patch when the same patch is excited with for example, unitary velocity. We have the pressure resulting directly from the source, that here we're gonna use a monopolar source of unitary velocity, for example, directly to the patch. And we have also the pressure at any given point inside the cavity that comes directly from the source. And we can use an analytical method as we are working with a homogeneous structure here, like the modal extension, to expand the pressure inside the cavity for any point, considering the shape and the amplitude of each mode involved in the cavity. And there's also a modes criteria that's already well established in the literature, that's going to be related to the size of the patches with respect to the size of the cavity itself. Okay. We also have to obviously describe well what happens inside the SBH through the impedance at the entrance of the SBH when we put, for example, a imposed velocity at the entry of the SBH. Here we're gonna have a 2D axisymmetric model made in FEM, for example. And as we're considering a geometry that gets more and more intricate as the origin of the SBH or the end of the SBH approaches, viscothermal losses are really important to be defined here. And this imposes to us another challenge, which is the fact that for viscothermal losses, we have to describe well the viscothermal boundaries. So that means that many elements are needed, especially at the end of the SBH when the dimensions are smaller, to describe well the viscothermal losses inside the SBH. So just to show you what a geometry like this delivers in terms of performance of the SBH itself. Once we have the impedance of the SBH, we can obtain the reflection coefficients. And in this case, we can see that until 200 Hertz or something, it drops. But then viscothermal losses becomes less and less important at the start of the SBH, and here we can see a little bit more of that modal feature that the real SBH is gonna have, because both axial and radial modes are gonna play a role here, and we know that radial modes are gonna appear as the frequencies are higher and higher, And we can see here that as the frequency increase, the cavities in between rings that are closer to the entry of the SBH are going to be more excited than the others. So as the geometry here is not favorable to viscothermal losses, that means that for higher frequencies, the performance of the SBH is gonna deteriorate a little bit. And it also shows the importance of trying another strategies to increase the performance of the SBH, like including, for example, absorbing material at some strategic places inside the SBH and that kind of thing. Once we have the PTFs of all subsystems, we can apply a continuity relation over the patches in between the subsystems. Obviously, let's consider this patch between the cavity and the black hole. The pressure at the both sides of the patch is going to be the same, and the velocity is going to have equal magnitude but different direction because of the normal, right? And we can characterize the pressure at the side of the cavity as being given by the pressure from the source and the pressure that comes from the coupled SBHs. Okay. And from the side of the SBH is going to be only the pressure given from the side of the SBH itself. And applying those two equations here at at our initial linear system, we can finally obtain the the coupled velocity in between the subsystems, and then with this coupled velocity, we can use it to have the pressure at any point that we want inside the SBH, considering also the pressure coming from the source. Okay. Finally, with the definition of the mean quadratic pressure inside a cavity, we can express it as a modal expansion too. And this is going to rely on modal mass and modal force of each mode. And I'm not going to open this very much because this is a very important audience that knows what I'm talking about. Now let us go to the validation of the PTF strategy with the FEM coupled system. In the left, we have the reflection coefficient of the original SBH, okay, which I already presented you. As the viscothermal losses are really important to characterize, we apply the linearized Navier-Stokes formulation to characterize the SBH. However, I don't know if that's so clear from your points, but if we use a strategy of, for example, placing a microperforated panel boundary in between the cavity rings like that, with these given properties, for example, of thickness and hole diameter and perforation ratio, we're gonna at the same time drastically improve the performance of the SBH. So we have the reflection coefficient here almost perfect. They're delivering almost perfect absorption, and the computational time, this time from the Helmholtz equation with the impedances of the microperforated panel characterized with mass formulation. Only a fraction of the time that took with the original concepts. And here it is important to notice that most of the losses are gonna occur at the surface of the MPP. So that's why the viscothermal losses lose importance somewhat. Now let us consider these actual system that were validated in terms of the FEM coupled model with an SBH with the MPP boundary. We can see here the two curves that were plotted for the FEM coupled model and the PTF model. We can see here that they are basically the same thing, but the difference is that the FEM model took almost 10 hours to run, and the PTF took 5 seconds, plus, all right, 6 minutes for the SBH characterization, and with a deviation that's almost nothing. Once the method is validated, we can do some parametric analysis to see what are the parameters of a system that are gonna really make a difference at the pressure, at the sound pressure inside the cavity that's gonna be calculated, okay? So from now on, we're gonna use only PTF. Here we have the blue curve considering for the former validated scenario. We have the blue curve being only the cavity without any SBH attached to it. And the orange curve is going to be the cavities attached with an SBH. Okay, so we can see already that there's a relevant difference for many peaks, many modes inside the cavity. And so at first, we're going to try and see what is the impact of the positioning of the SBH on the top surface of the cavity. So we start with the nominal case, let's say, which is near the corner. And then we try at the center, at this line here, and at the center of a quadrant like this. Okay? And let us concentrate on a given peak that's quite interesting because the effect of the SBH is noticeable. This frequency here. Here we can see that from the isopressure curves that were plotted inside the cavity. Here we can see that obviously this configuration here delivers the most reduction for this frequency here. As we can see, there is a high pressure region here, so this SBH is expected to couple really well with the cavity. However, if we position the SBH, for example, here at the middle of the cavity, this is gonna be a nodal line for this mode. So as expected, we're not gonna see that much of a difference because the coupling is bad. And the same kind of analysis can be made for the other two locations. And aside this specific frequency, we can see that in general, if we see the third octave levels for the cavity alone and the other four configurations, in general, especially for low frequencies, this configuration here of the black hole at the corner of the cavity deliver the most reduction in general. And as we can see, all right, this is only for a peak, but this kind of trend is observed for many frequencies at the range, okay? We also made a parametric study of a number of SBHs attached to the cavity. So from the nominal case, we go to 2, 4, and 8 SBHs, always observing that trend of trying to place them near the corners, okay? And for the same frequency, as you can see here, now we have a more linear trend of, okay, once you increase the number of SBHs, obviously the coupling with the cavity is going to be more important and the reduction of the pressure in the cavity is going to be more important. Now we have up to almost, let's say, 8 dBs of reduction for a given third octave band. And once more, at the lower frequencies, the effects of the SBH are more pronounced. And aside of that, we also came up with a new idea of coupling an SBH to the cavity, considering that it doesn't make much sense geometrically to put like something that looks like a chimney on a cavity, you know. So because of these geometric constraints that often are the case in real applications, we try this horizontal SBH here. And The characterization of the SBH itself delivers this as a reflection coefficient for the SBH with the MPP boundary. So we can see that it's basically the same dynamics in what's matter for us, which is the absorption. And also the results of the coupled system considering the vertical and the horizontal SBH is pretty much the same thing once more, which makes us think that this new design is possible to be applied without any repercussions in modeling. So for this first paper, a numerical procedure based on PTF to couple SBHs to a closed cavity was developed, and it was found an excellent convergence with the FEN model, but for a fraction of the calculation time. Parametric analyses were made considering position and number of the SBHs, and we found that the corners of the cavity are generally better for reduction of noise and a great efficiency over low and medium frequencies. And for future work, experimental validation, voila, that's what we're trying to do now. And more complex scenarios are from acoustics and other applications. So just quickly going, because I'm already over time, to the second paper that is being produced, experimental validation of the coupling between a sonic black hole and a resonant cavity using PTF. During my time in Barcelona, I was able to build a reverberant cavity in wood and metacrillate panels inside to diminish the absorption of the wood walls. And with this SBH that was produced by a former Laurent student from the PRI, Timothée Maillard, we could make some experimental studies of the coupling between the SBH and this cavity. So just to show you quickly the characterization of the SBH itself, it was made with an impedance tube. And here we can see the comparison between the linearized Navier-Stokes FEM model to characterize the SBH and the experimental characterization, which is really good. This for the absorption of the empty SBH, and this for the absorption of the case 2 is how we call SBH with melamine filling in the cavities of the SBH. Okay, so here we can see that the absorption is almost perfect. And we put this setup together, this experimental setup together, and many different locations, possible different locations for the SBH, but up until now only the northeast and the west position have been tested. And 38 points inside the cavity over 2 rods, one here and one here, that allow me to vary the radial position of the microphones and everything to do the measurements. And a simple setup, a MATLAB script that sent a function for the data acquisition system that sent this sweep function to an amplifier, and then the amplifier excited the speaker of the impedance tube, and the impedance tube is going to excite the interior of the cavity, and we're going to have readings for the 2 microphones to after do the post-processing, okay? Obviously, we're going to have to compare that to the PTF model of our cavity here, and we're going to have for this PTF the impedance tube open end, which is gonna behave almost like a monopole for the source, given the dimension of the hole here, okay? And we're gonna have analytical PTFs for the cavity, since once more it's a homogeneous structure, and the experimental characterization for the SBH as PTFs. And after we're gonna analyze the mean quadratic pressure, considering the 38 microphones inside the cavity for the lower frequency. region, which is closer to the cavity first mode, and it's more important for us considering our previous paper findings. So just to show you quickly here, we have as experimental results for the northeast and the west configurations, northeast and west. We have in black the response of only the cavity. In red, the response of the cavity coupled to an empty SBH, and in blue with the SBH with melamine filling. And we can see here that, for example, for this SBH, which is closer to the corner of the cavity, as we found in the previous paper, there's a big difference from some peaks here, for example. For this mode here, probably there's a nodal line that goes close to this placement here, and we can also observe the difference that happens between the empty and the case 2 SBH. Here, for this and this peak, we have quite a surprising but explainable results, as the case 2 SBH, that is the SBH that has theoretically more absorption, performs worse than the empty SBH. And we are still, we have some hypotheses, but we're still explaining that. And we also have the modal expansion basis for the cavity, which is totally comparable to the experimental results, as you see here. And we ran some PTF codes for the configurations with the SBH to see if we were able to characterize the what was happening when we couple the cavity to the SBH with respect to the experimental results. And here we can see that the trend is really well characterized, although for the magnitude there are a few differences here and there. And the same thing with the west configuration. And here we probably have a numerical mistake here, because this first mode, I have a figure for it, but I don't think that we're gonna be able to talk much about it, because I'm way over time now. But for this peak here, which is the first mode, that has equal pressure theoretically for this whole part, the top part, the west configuration totally kills this mode, and it doesn't make much sense from our point of view. But anyway, we're still evaluating these results. So far, we see that PTF is capable of reproducing the dynamics that were characterized experimentally, but the pressure magnitude by PTF is often overestimated. And once more, the placement of the SBH is found to play a role in the cavity's dynamics, as shown in the previous paper. So this is the part where I put some, like, to each mode, each peak would correspond, but I think this is more intricate analysis that could be done maybe in another moment, or anyway. So that's it. These are the references that I used. If you want, I can send it out to you. And thank you all, and n'hésitez pas si vous avez des questions. Merci.